Okay, so yeah, this week's agenda, find the cosets of the subgroup generated by 3 in Z12, show that left cosets and right cosets don't need to be equal, show that the converse of Lagrange's theorem is not true, and use Fermat's theorem to compute some exponents, mod p. Okay, so the cosets of 3 in Z12. So the left cosets, I'll say, but the left cosets and the right cosets are the same. Okay, so first of all, what's the subgroup generated by 3? It's 0, 3, 3 plus 3, 3 plus 3 plus 3. Okay, now how do you get cosets? You just apply an element of the group on the left. So 0 plus 3, you apply 0 on the left. So it's 0 plus 0, 0 plus 3, 0 plus 6, 0 plus 9, which is just same subgroup again. What about 1? You get 1 plus 0, 1 plus 3, 1 plus 6, 1 plus 9, which is 1, 4, 7, 10. What about 2? 2 plus 0, 2 plus 3, 2 plus 6, 2 plus 9. So you get 2, 5, 8, 11. And note that they're all disjoint. I think that should have been something you've proven in class. And then if you do more elements, you actually will just get the same cosets back. So let's show that. So 3 plus 3, 3 plus the subgroup generated by 3 is 3 plus 0, 3 plus 6, 3 plus 9. 3 plus 3, 3 plus 6, 3 plus 9, which is 3, 6, 9, 0, which is the same thing as 0, 3, 6, 9. Order doesn't matter. So that's just, you just get the subgroup back. 4 plus 3. So that's 4 plus 0, 4 plus 3, 4 plus 6, 4 plus 9. So it's 4, 7, 10, 1. Same thing as 1, 4, 7, 10, which is the same thing as 1 plus 3. 1 plus subgroup generated by 3. 5 plus 3. So you get 5 plus 0, 5 plus 3, 5 plus 6, 5 plus 9. So you get 5, 8, 11, 14, which is 2. And then 6 plus 3. Again, you get the same subgroup back. So 6 plus 0 is 6, 6 plus 3 is 9, 6 plus 6 is 12, which is 0 in Z12, 6 plus 9 is 15, which is 3 in Z12. So again, you get 0, 3, 6, 9. Okay, and I could continue this, but I won't, because I think it's easy to continue this, so you could see for yourself what you would get. And what you get is this. So you get that if you apply 0 plus 3, if you apply 0 on the left, or if you apply 3 on the left, or if you apply 6 on the left, or if you apply 9 on the left, you just get the same subgroup back. If you apply 1 on the left, 4 on the left, 7 on the left, or 10 on the left, you get this coset. And if you apply 2, 5, 8, or 11, then you get this coset. And those are the 3 cosets. So every element of Z12 belongs to one of these cosets. So we can note a couple of things that are examples of the general theory of cosets. So should I write? So we can see a couple things which are examples which generally hold for cosets. So one thing is, the cosets partition the group. So they split the group into disjoint sets. Sets of size H. Okay, I should write for the cosets of a subgroup H of G. I'll rewrite that. I was not happy with that sentence. Okay, so we, in this example, we saw a couple things that generally hold for cosets of a subgroup H of G. So number one is the cosets partition, i.e. split into disjoint sets. They partition G into sets of size H. So whatever the number of elements of the subgroup is, all the cosets have that number of elements. And so you partition G into some sets that all have the same size. And so in particular, well, first I'll write what the sets are in this case. So in this case, 0, 3, 6, 9, 1, 4, 7, 10, and 2, 5, 8, 11 is a partition of Z12, right? It's a partition of Z12 into 3 sets of size 4, right? So Z12 is just all those elements. It's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. If you look at the cosets of H, it always partitions the group into some number of sets. And the number of sets is always G over H. So in this case, it's number of elements of Z12 over the number of elements in the subgroup generated by 3. So it's 12 over 4, which is 3. So since you partition into subsets of size equal to the order of H, the number of sets you'll get is just the total number of elements divided by the number of elements in H. So that always happens. And note that I write cosets, it's because it could be left or right. So just remember that if you're working with cosets, just pick either left or right, and then always work with either left or right. As long as you don't mix them together, there's no issue. So this applies for left cosets and it also applies for right cosets. Okay, and another thing we saw is that for any element A in H, AH equals H. And even though we didn't see this directly, Also, if you apply it on the right, it's the same thing. Also, HA equals H. So if you apply an element of H to H, you get back H. And this is a consequence of H being a subgroup. So in our example, we saw that 0 plus 3 is the same thing as 3, the same thing as 6, which is the same thing as 9. So if you apply an element of the subgroup, then you just get back the subgroup. And another thing we saw that's actually a consequence of 2 is that for any element A in H, BAH equals BH. And also, even though we didn't cover this, it's true for basically the same reason. So anything that's true for left cosets, there's something analogous that's true for right cosets, because there's very similar objects. So HAB equals HB. Okay, and well, this actually is a consequence of 2. I mean, 0.2 written above, because AH equals H implies BAH equals BH, right? And we saw it in our example. So in our example, we had like 1 plus 3. And then if we do 4 plus 3, well, 4 plus 3 is the same thing as doing 1 plus 3 plus 3. I mean, plus the subgroup generated by 3, which is just 1 plus subgroup generated by 3, because 3 plus the subgroup generated by 3 is a subgroup generated by 3. 7 plus the subgroup generated by 3 is 7. It's 1 plus 6 plus the subgroup generated by 3, which is 1 plus the subgroup generated by 3. 10 plus the subgroup generated by 3 is 1 plus 9 plus the subgroup generated by 3, which is 1 plus the subgroup generated by 3. That's a mouthful. Yeah, so it's what we saw, right? So for each element of the group, you get a coset, but some elements generate the same coset. And precisely they do when they differ by an element of the subgroup. So 1, 4, 7, and 10 all give you the same coset. 2, 5, 8, 11 all give you the same coset. It's because they all differ by an element in the subgroup. So 2 and 5, 5 is just 2 plus 3. So adding 5 is just adding 3, which doesn't change the subgroup, and then adding 2. So that's something we saw. And so I guess I'll write what I just said in words, which was, what was it? Oh yeah. So each element of the group G gives you a coset, but some of these cosets are equal. Precisely, to be precise, for each element, there are H elements, the number of elements in H elements, which give the same coset. Right, so for 1, it's 1, 4, 7, and 10 all give the same coset. Because you could do 1, or you could do 1 plus 3, or you could do 1 plus 6, or you could do 1 plus 9, and they will all give you the same coset, the same left coset. And the other way works too. For right cosets, it's HAB. So this thing generally holds for cosets in even non-abelian groups. Okay, so that's all there is to this example, but it's a good segue to point 2. So that left cosets and right cosets are not necessarily equal. So that's something we didn't see in this example because it's an abelian group. So in an abelian group, they are equal. So I didn't calculate the right cosets, but if I did, they would have been equal in our example before. So example, in Z12, let's do 2 plus the subgroup generated by 3. That's just going to be 2 plus 0, 2 plus 3, 2 plus 6, 2 plus 9, which is 2, 5, 8, and 11. If you do the subgroup generated by 3 plus 2, you get 0 plus 2, 3 plus 2, 6 plus 2, 9 plus 2. But I mean, addition doesn't matter what order you do it in. So you again get 2, 5, 8, and 11. So 2 plus 3, 2 plus the subgroup generated by 3 is the same thing as subgroup generated by 3 plus 2. But in non-abelian groups, i.e. in groups where AB does not need to be the same thing as BA, so whenever the group operation is plus, that means it's abelian. Like they wouldn't even write plus if it weren't abelian. But there are non-abelian groups, and in non-abelian ones, they don't have to be equal. So let's do an example. Example, let G be D4 and let H be the subgroup generated by D. So recall that D4, the elements are the identity, then there's 3 reflections called, 4 reflections, I mean, called D, H, V, and D prime. And then there's the remaining rotation, so R90, R180, and R270. And if you don't remember D, H, V, and D prime, so D is the one that reflects on the main diagonal. So that's D. And then D prime is this one. H is the horizontal line. That's why it's called H. And V is the vertical line. Okay. So that's D4. And the subgroup generated by D, so H is just subgroup generated by D, which is just the identity and D. Because D squared is just the identity, right? So the subgroup generated by D is supposed to include all powers of D, but D is a reflection. So there's just D and the identity, because D squared is the identity, D cubed is D fourth, D to the power 4 is the identity. So, you know, that's all there is in the subgroup. So I guess I could write that down. So D is supposed to be it's supposed to include all these powers of D. But really, if you look at all the powers, you just get the identity in D because D is a reflection. Okay, now what are the cosets? So let's find what is, let's say R90 times the subgroup. So R90 times D, you just apply R90 to each element. So you do R90 times the identity and R90 times D. So you get R90 and R90 times D. What is R90 times D? Okay, so to calculate it, I want to do a quick aside. How do you quickly do computations in the dihedral group? Okay, I'll be more specific than that. How do you quickly find a product in the dihedral group? There's 2 steps. So step 1, figure out if it's a reflection or rotation. So remember, reflections cancel out. So a reflection times a reflection is a rotation. Reflection times a reflection times a reflection is a reflection. It's like multiplying -1 and 1. And then step 2 is follow a single vertex. So this isn't that efficient, but it's more efficient than following every vertex. So just figure out if it's a reflection or rotation, and then follow a single vertex under the product and see where it goes. And it's best to pick a vertex that's fixed by some reflections. So then you have to do less work. Okay, let's apply this to R90 times D. So R90 times D, step 1, it's a rotation times the reflection. So it's a reflection. Step 2, I'll follow a vertex. So I'll follow vertex. I'll follow this vertex because it's not moved by D, right? So if I apply D, it doesn't move. So it's a convenient vertex to pick. Now if I apply R90, it goes here. So overall, which reflection sends this vertex, this vertex that I picked, which reflection sends it here? The answer is H. Right? Because, you know, if you apply H to then that vertex moves to the location we wanted to move to. Okay. So yeah, that's how you can find a product slightly faster. So, but going back, we have R90 times the subgroup generated by D. Is R90 and R90 times D, which is R90 and H. On the other hand, what's the right coset? So it's going to be R90, and I mean, I'll show you step by step. So first you write the elements, and then you multiply each one by R90 on the right. So the first element's the identity, and then it's D times R90. And then the identity times anything is just that thing again. So this is R90, this is D times R90. And then I find D times R90, so I know it's a reflection. I'll follow this vertex. So under R90, it goes here. And then I purposely picked it so that it'll get fixed by the application of D, just to make my life a bit easier. So there, so which reflection sends this to this? The answer is V. Okay, so D times R90, I mean, subgroup generated by D times R90 is this set, whereas R90 times the subgroup generated by D is this set. So the left coset and right coset aren't equal. Are not equal. And the reason was that, and this can only happen in a non-abelian group, like D4. Note, however, that a non-abelian group, all that implies is that two elements don't commute. It doesn't mean that every two elements don't commute or something. So there could still be left cosets that are equal to right cosets, and there often will be, because anytime you have a normal subgroup, all its left cosets will be equal to its right cosets. So I'll write that down. So they could be equal, but they don't have to be equal. They have to be equal in an abelian group. So again, we'll use the same example, but instead of R90, we use R180. So D times R180 is R180 and this, whereas R180 times the subgroup generated by D is R180 again, but then R180 times D instead. With the R90 case, it was the same. And the reason the two cosets ended up being different is because D times R90 is not R90 times D. But for R180, they're actually equal. So things can commute in a non-abelian group. I mean, obviously, like in the dihedral group, for example, it contains an abelian group inside it. It contains the rotations, which all commute with each other. But yeah, even a rotation and reflection could potentially commute with each other. So let's see. D times R180 is, okay, we know it's a reflection. I'll follow this vertex. So under R180, it goes here. And then under D, it stays where it is. And I purposely picked a vertex that would stay where it is to make my life easier. And R180 times D. Okay, so which reflection sends this to this? It's D prime. And the same would be true for R180 times D. So apply it to this vertex. If I apply D, it stays where it is. I want that. And then if I play R180, it goes here. So it's the same thing. So that means both the left coset and right coset are equal. So R180 times D, the same thing as D times R180, which is R180 and D prime. And note again that the general things that I said about the theory of cosets hold here as well, right? So the cosets of D partition D4, which has 8 elements, into 4 sets of size 2. And some elements generate the same coset. So, and that's something we saw, that was a general remark made. And so D, first of all, any element of a subgroup, just the coset will just be the subgroup itself. So D times D equals D. Also, 2 elements that differ in quotations by an element of the subgroup generate the same coset. So what's an example? R90 times D is the same thing as R90 times D. And what's R90 times D? We already found it, so I'll just go back. It's H. So R90 times D, so I'll rewrite this actually. R90 times D is the same thing as H times D, because H equals R90 times the actual element D, not the subgroup generated by D. And I don't know, what's another one we did? Oh yeah, we did the right coset. So it also works for right coset. So D times R90 is the same thing as V, D times V, because V is D times R90, right? So if you first apply an element of the subgroup, it doesn't change the subgroup, and then you apply R90. So applying V is the same thing as applying R90. Okay, so that covers this example. Next. So next we want to show the converse of Lagrange's theorem doesn't hold. So Lagrange's theorem is just a consequence of one of the remarks I made about the general theory of cosets. So it's one of those theorems that's easy to prove once you develop the theory. So in particular, the theory of cosets. Once you understand what cosets are, it's kind of just an obvious theorem, because it says that for any subgroup H of G, the number of elements in H divides the number of elements of G. And the reason is that G splits into sets of size H, namely the left or right cosets of H. So it has to divide the number of elements of G, right? Like, could I have a group of size 72 with subgroups of size 5, with the subgroup of size 5? No, because if I took the subgroup, the cosets of that subgroup, they each have 5 elements, and they would have to partition 72 elements. That's not possible, right? Like, you can't have disjoint sets of size 5 totaling 72. It just doesn't work. So that's why Lagrange's theorem holds. So it's a simple consequence. Once you understand how cosets work, Lagrange's theorem is a simple consequence. And the converse would be for group G and a divisor D of the number of elements of G, does there exist a subgroup H with D elements? So Lagrange's theorem says the number of elements of a subgroup has to be a divisor. The converse would be, for any divisor, is there a subgroup with that number of elements? The answer is no. The answer is no. So in particular, if G equals D4, not D4, A4, so the alternating group on 4 elements, the even permutations in S4, then there's no subgroup. Well, first of all, then G has 12 elements, and 6 is a divisor of 12, but there's no subgroup of size of G with 6 elements. And I'll prove it. So proof. So first note that A4 is this. It's 1, 2, 3, 1, 3, 2, 1, 2, 4, 1, 4, 2, 1, 3, 4, 1, 4, 3, 2, 3, 4, 2, 4, 3, 1, 2, 3, 4, 1, 3, 2, 4, and 1, 4, 2, 3. And the identity, of course. And if you don't know how I just came up with that, I recommend reviewing the parity of permutations, like evenness and oddness. But just to give you a quick recap, a cycle of length L, it's a product of L minus 1, 2 cycles. And the total number of 2 cycles gives you whether the permutation is even or odd. So a 3 cycle is 2 cycles. So any 3 cycles even, and obviously any product of 2 cycles is 2 cycles, so it's even. That's the only way, and the identity is always even. And that's the only way with 4 elements. You can think about it, but there's no other way to get. I mean, the only other possibility is just a 2 cycle, which is odd, or a 4 cycle, which is 3 2 cycles, which is odd again. But yeah, I recommend reviewing that material if you're not comfortable with that kind of reasoning. So yeah, assuming you are, then you can find A4, and it's going to be this. So it has 12 elements. Now, suppose for a contradiction, that A4 has a subgroup H with 6 elements. Also, I should let you know that this is an argument from the textbook. So this is from page 144 in the textbook. So suppose A4 had a subgroup H with 6 elements. So, and then the idea is to consider the 3 cycles in A4. So we know there are 8 3 cycles in A4. Since H has 6 elements, some 3 cycle A, okay, I'll call it X, must not be an H. So now let's look at the cosets of H, right? Since H has 6 elements, and A4 has 12 elements, and I'll pick left cosets. Always just pick one, left or right. So A4 has 12 elements. there are 12 divided by 6 equals 2 left cosets of H. So, and remember the left cosets partition the whole group, right? Partition means split into disjoint sets. So therefore, we actually know what the two cosets are. So the two left cosets are H, which has 6 elements, and then everything not in H. Which again has 6 elements. And we can give everything not in H a name. So everything not in H, since X is not in H, the coset, the left coset, XH must be everything not in H. Okay, so it goes back to a fact I said before. So if you do A times H for an element of H, you just get back to subgroup. I guess I only said this as an one direction, but it goes both directions. So if you multiply a subgroup by an element and get the subgroup back, then that element was in the subgroup. So I should write that down. In general, XH equals H if and only if X is an element of H. Okay, so the left coset XH, since it's not H, it must be that other coset. There's two left cosets, right? The cosets must partition the original group. So since H has 6 elements, there's only 6 elements left, so that must be the other coset. So there's 2 cosets, there's H, and there's just everything not in H. And then, so XH is one of those cosets, right? Like every element gives you a coset, but some elements might give you the same coset. So XH is going to be one of those cosets, and we know it's not H, so it has to just be everything not in H. Okay? But now, note that X squared is also not in H. Why? Because X has order, X is a 3 cycle. So if X squared is an H, then X squared squared would be an H, which is just X to the 4. But X to the 4 is X times X cubed, which is just X. Which is because X cubed equals the identity. Right? Like, for example, if X equals 1, 2, 3, if 1, 3, 2 was an H, then, you know, H is a subgroup, it's closed under multiplication. So 1, 3, 2 squared, which is 1, 2, 3, would be an H. Right? So since we're assuming X is not an H, that means X squared is also not an H. Because if X squared were an H, then X would be an H. Note this only works, so I'll write that down. Note this works because X has order 3. In general, you could have X squared being an H, but X not being an H. That's possible in general, but because X has order 3, it's not possible here. Okay, so both X squared and X are not in H. And that means x squared times H must be x times H, which must be the other left coset, the coset that contains everything not in H. But this is impossible. X squared, the coset for x squared cannot be the same thing as the coset for x. Why? Because if x squared is an element in, if x squared times H equals x times H, then that means x squared and x differ by an element of H. So that means then x squared must be equal to x times H for some element H in H. I mean, this goes back to a fact I said earlier. Again, maybe I should have wrote it differently. All these facts are if and only ifs. So, you know, like if two cosets are the same, that means those two elements differ by an element of H and vice versa. So I only wrote one direction here. If you have an element A and H, the coset BH is the same thing as the coset BAH. So multiplying B by an element of H gives you the same coset. And it also works the other way around. So here, if x squared and x give the same coset, that means x squared must be x times some element of H. But solving x squared equals xh gives h equals x, right? That's the only way you can write x squared as x times something. It's just x times x. You can solve equations in groups, okay? So x squared equals xh. It's like how you would solve equation normally. If you had like 2x equals 4, you would divide both sides by 2. Here you divide both sides by x. So you do x inverse times x squared equals x inverse times x times h. So then you get x equals h. So therefore, x equals h, which is an element of the subgroup H, but we assumed that x is not an element of the subgroup H. We have a contradiction. Hence, there is no subgroup H of A4 with 6 elements. So that's all I can get through this week. Thank you for listening.